this video. Okay, you need to record this video so that you can review what has been explained. Okay. So another reminder, okay, just another reminder that next Monday we will do EM1 and AMM quizzes for week 3 with HBL. That's the main thing. So bring your lecture notes, both EM1 and AMM, to school for me to just have a look, and also bring your EM1 tutorial, the assigned homework, okay, that the HBL assigned you to do, so that I can just have a look at it. Okay, so now I want to address some of your questions that you asked in the essay ticket. So, okay, the first question is kind of an important one. All right. So, one of you asked is, or to the same effect, okay. So, one of you asked this, is the interval 0 to infinity the same? I might be misunderstanding, but I think the main thing. Oh, sorry, it's not a round. It's supposed to be a round bracket. Yeah. So it's, if you put 0 to infinity and it's not including 0, is this the same as 1 to infinity? All right. Or is it the same as R plus? So what do you think, guys? Is this the same? Will this be the same set? Yeah, you're right. Okay, it's not, and it's best that we visualize this on the number line. I think specificity is over here. Okay, R plus. Let me just say R plus is the this one. This is R plus. Okay. So it's actually the same as 0 to infinity, positive infinity. 0 is and 1 to infinity starts from here. Okay, 1 to infinity starts from here. Okay, that there's some empty space. Just because you don't include 0, doesn't mean that it's the same set. Okay, there's still some empty space over here. There's still some empty space here. Okay, there are numbers which are smaller than 1, but they are not the same sets. Okay, not same sets. So this is wrong. That's the first thing. I think this is a common mistake that students make. That they forget that they are actually numbers between 0 and 1. Real numbers between 0 and 1. Okay, so that's one. Second question is concerning absolute value. Okay. So one of you asked, so that's the first question that I found. Second question is that so yeah, so the R plus 1 is correct. The R plus 1 is correct. The second question is asked this. Okay, so is piecewise function, other than my handwriting. Okay, is piecewise function the same as absolute value or magnitude or modulus? Is it the same as absolute value function? The answer is no. Okay. Absolute value function, okay, absolute value function, right, is a special type of piecewise function. Okay, so you can see this is a special type of piecewise function. This is a piecewise function, or rather I would say this is an example. Okay, it's an example of a piecewise function. This is an example of a piecewise function. So absolute value function is not, piecewise function is not an absolute value function. Okay. The absolute value function is just an example. There are many other types of piecewise functions. Okay, is that understood? All right. So they are not the same concept. Okay, a piecewise function and absolute value function are not the same things, but we can say that absolute value function is just an example. Okay, specific case, a special type of piecewise function. It's as though there's a huge set of piecewise functions, and absolute value function is just one member inside this set. Something like that. Okay, for the last question, I think go to show you my lecture notes, because there is a question concerning the video. It's one of the examples in the lecture notes. So just let me show you my lecture notes. Okay. Okay, guys, do you see the Word document? You guys see the Word document? Right. Okay. So what someone asked, okay, why do some graphs have a horizontal line attached to the linear line y equals mx plus c? I think this is a question concerning example 22 over here. Right. Do correct me if I misunderstood the question. Okay. So I think he was asking, okay, this is a horizontal line, right? This is a horizontal line over here. Yeah, was for absolute value equation, yes. And this one is the y equals mx plus c. This one over here. This is horizontal. So the question was asked, why do some graphs have a horizontal line attached to a linear line? Well, it's just, the answer is that it's the definition of this particular piecewise function. So basically the example 22, the piecewise function, yeah, it's called gx, sorry. It's not f, it's called gx. Piecewise function consists of one line. Okay, a horizontal part, the yellow part, means it's a constant. Okay, it's a constant number. And then this third piece is also another line. Okay, so this piecewise function comprised of three components. This one, the horizontal one, it just means it's a number, and then there's this straight line over here. Okay, I hope this answers your question as to why there's a horizontal line. The horizontal line just indicates the constant value. Okay, let me maybe write it out here. Horizontal line indicates horizontal line indicates constant value. Right, let's wait for Deba to ask a question. If there are any other questions, please feel free to type it in the message. So, we would write instead that value x is equals to x. Right? X is more than 0. More than or equals to 0, and then less than infinity. Not less than x. Yeah, that's right. Greater than or equals to 0. That's right. That's true. That's right. Yeah, that's right. So 1 is if it's more than 0, and 1 if it's less than 0. Nope. Although it looks like negative, we've been through this before, although it looks like negative, right? So I would say here, although negative x, if x is less than 0, looks negative. Okay, actually in actual fact, let me just show you with a precise number. Let's say negative 5. If x is equals to negative 5, alright, then negative of negative 5 is actually equals to 5, which is greater than 0. Okay, so if x is equals to negative 5. No. I mean, it's just like this. Let's say you are evaluating a negative modulus of a negative number, let's say negative 5. Okay, all you will do is just follow along. So negative 5 is a negative number, so you use the formula negative x. Okay, but then negative x is actually equals to negative 5. So that will be 5. Okay, you don't substitute the negative x into the modulus. You substitute the number into the x. That's what's happening. This whole thing, this entire negative 5 is substituted inside here. And that's what you see exactly. It won't be negative numbers. Basically, this thing is not negative. It's not a negative number. Alright. Okay. Are there any other questions? If not, we have to go on to our lectures. I'm going to show you the lecture notes now. Okay. We are at page 27. Okay, everyone, we are at page 27. We're going to talk about inverse functions today, this morning. Okay. So inverse functions. So what are inverse functions? Okay, inverse functions Okay, let's say you got a function, all right? Let's say, remember, function is some kind of machine that you can dump an input into it. All right? You just dump an input, say x. Okay, you dump an input into the machine function, into the function machine, so it works, and out comes y as an output. Now, because you learn about composition of functions, we can do this. We can take the output of y, okay, we can take the output y, and dump it into what we call the inverse function machine. Okay, the inverse function. This guy over here, f to the power negative 1. So this is the inverse function. Fn for function. Okay, you can take the output of y. You can take the output y over here, and just put it into the inverse function. And what does the inverse function produce? It actually produces out the original input x, okay, that you started off with. Okay, that's what the inverse function is supposed to do. Just like f to the power negative 1. Okay, say again. So you start with some input x, which goes into the function machine f, and f will produce an output for you. But this same output, okay, this very same output from f, we will dump it into the inverse function, and the inverse function is supposed to return you the input that you started off with. Okay, that's what the inverse does. It returns, for a given output, it returns to you the original input that you started off with. Okay, so if I write this in terms of composition of functions, so it starts off with x, okay, and then f takes on x to produce fx for us, and then you compose this with f inverse. So f inverse takes in fx, you see that? F inverse takes and produces x. Okay, so another way of writing is that f takes x, okay, so f takes x, and f inverse takes on fx. So what does f inverse do to fx? It produces x. So that is what an inverse function is supposed to do. Alright. You guys have an idea of what inverse function is supposed to do? Is this okay? So I just give you an example. Let's say your function, whatever it may be, takes in the input 3 and produces 8 for you. So what is the f inverse supposed to do? Well, guys, we look at this box over here. 3 goes into f, okay? You see 3 goes into f, and according to this equation, it's supposed to produce 8. 8 comes out. So what does f inverse do to 8? Okay, what does f inverse do to 8? F inverse will take 8, it will go inside f inverse machine and process, and out comes 3. Okay. So that's what those abstract things mean. F takes 3 and produces 8. But what does f inverse do to 8? F inverse takes 8 and produces 3. Because 3 produces 8, so f inverse just reverse the whole process. Now guys, we can also start with f inverse first. For example, we can look at this. Right, I pause here first. I wait for Java to try to finish his question. Anyway, anyone got any question? Just ask freely. Java, you have a question? Yes, yeah, you're right. That's one example of use of inverse function, sine and inverse sine. Alright, that's one example, yes. So like cosine and inverse cosine, or tangent and inverse tangent, okay, those are examples of inverse function. So for the sine case, okay, or let's say sine, okay, let's say you have sine pi over 3, that's 60 degrees, so that's root 3 over 3, okay. So what does inverse sine of root 3 over 2 do? Okay, it returns to you pi over 3, something like that. Just as the way sine inverse works on your calculator. It takes in the ratio and returns you the angle. Usually for trigo function, it takes in the ratio. Now it's the other way around. Okay, so that's what the inverse function does in general. So cosine, okay, what is cosine pi over 3? So we all know that cosine pi over 3 is half. So what is cosine inverse half? It's just pi over 3. So it's precisely the way your calculator works. Okay, just to finish off this page, now guys, we can also start with F inverse. You see over here, F inverse. You see we're starting with F inverse, so this is the other box now. So we can study what happens if we put in 8. So F inverse takes in 8, right? 8 goes into F inverse. And it's supposed to return you 3. Okay, but now what does F do to 3? Okay, what does F do to 3? Well, F is supposed to take 3, and lo and behold, it returns you 8, just as it's written up here. Alright, huh? Okay, so F actually will inverse what F inverse does. Okay, or rather, you can think of it this way. I can start with F inverse, and it takes in X. Okay, so what does F do to F inverse X? It actually returns to me X. Okay, so let me just get rid of all these little scratches. So guys, these are two equations which are important. So it's this one, this second one over here. Take note especially of the order in which I write the F and F inverse. Okay, both of this must be true. Okay, if a function has f to the power negative 1, both of these equations must be true. In the yellow box, comes first, f comes first, then followed by f to the power negative 1. The green color box, f to the power negative 1 comes first, then followed by f. All four formula represent the same thing. Not sure what you mean by that. Okay, as we go on, I think it becomes clearer. Then maybe once you a better idea, then you can ask clearer picture, clearer question. Yes, so let's see, fx is 3x plus 2, so yeah. No, that's not simple. That's not one. The f to the power negative 1 is not the reciprocal, okay? It's not the reciprocal. It's something else. There's another way in which you will calculate the formula for f to the power negative 1. But it's not 1 over 3 as plus 2. Alright? Okay, let's go on to the example which will help to clarify some of these issues. So example 26, okay. um, I want someone to help me do this. You guys look at the first. See, anybody which I'm going to give you control of enable you to scribe on this Word document. Okay, anyone. Okay, Java volunteer. Yes. So Java, can you look at F? Alright, and then in the second box here, can you draw arrows to represent F inverse? Just use your mouse and try and draw the arrows for F inverse. Okay. And yes, very good. Okay, that's fine. Alright, so that's true. Okay, that's good. So what you see is basically the arrow diagram for F inverse. Okay. So let's just check. Okay, this is F to the power -1. Okay. So guys, we look at this test out. Okay, one example. So F of 5. Okay, we are looking at 5. Where does 5 map to? 5 maps all the way up to -5. Okay. And well, we have -5 that goes now into the F inverse, and where does -5 end up with? Oh, it ends up at 5. So actually we started off with 5, we went through F, alright, okay, went through F inverse and ended up with 5 again, where we started off with. So F of 5 and then F of inverse of F of 5 really is 5. And you can test out for the others 1, 2 and 8 as well. So this arrow diagram is really the inverse function of F. Okay. Now let's look at some situations where it may not be possible, okay, to actually have an inverse function. And guys, we look at G now. Look at G. Exponent function e to the power x is an example of an invertible function. Why don't you try and figure out what is the inverse of the e to the power x? E to the power x. And that's another example of an exponential function. Okay, e to the power x, its inverse, as can we say, is the log. Oops. Not the woman in the red dress, but log of x. Okay guys, let's look at G. And now if let's say we try to fill up the arrows, okay, I'm going to fill up the arrows for you, and then you tell me whether G inverse is a function or not. Okay, so let's just look at G inverse. Okay, so we look at 1. Okay, so 1, if I'm trying to revert things, it seems that 1 has to point to 7 and also point to 3. 0 will point to negative 5 and 2 points to 11. Okay guys, can you tell me, is G inverse a function or not? Yeah, it's no inverse. Okay, I think the problem really lies here. I'll just highlight it. If the problem really lies here, if you look at 7 and 3, they map to one single output, which is 1. So when you look at G inverse, the problem becomes that 1 suddenly must map to 2 guys, and this is not a function. Okay, you cannot have a single input mapping to 2 outputs. So G inverse is not a function. Yeah, it's a relationship. That's right. So this is no good to us. So we say that because it as a function is not invertible. Okay. And if we compare this with F, all right, what's the differences between F and G? Okay, what are the differences between F and G? You notice that in G you have 2 inputs that map to the same output, whereas in F every input has its own output. Okay, I will say that every input, let me just write like this. Okay, one input, one output. So one input, yes, that's right, one output. That's F. Whereas in G, 2 inputs to 1 output. So you see that? That's the main difference between F and G. And I think you all can see that for F inverse, it's really necessary that 1 input maps to 1 output. Okay, because every output has a unique input mapping to it. Okay, I'm going to write here. Let's get this down. Okay, every output has 1 unique input mapping to it. 1 input to 1 output. Okay, whereas G, you see 2 inputs mapping to 1 output. So because of this crazy situation, this bad. Okay. You see that G is not invertible. But for F, because 1 output has a unique input mapping to it, it has an inverse. You can easily construct an inverse. Okay. Now we give a special proper name to this property of 1 input to 1 output. We call this 1 to 1 function. F is a 1 to 1 function, whereas G is not a 1 to 1 function. Alright. So we learned something. We learned an important fact just now, that for a function to have an inverse, okay, or for the inverse to be a function, or to say that if F is invertible, it is necessary, okay, for F to be a 1 to 1 function. Okay. Just write here. Okay, let me just write it here in the messaging box. Okay, so you can comment if you want to. For F to have an inverse function, necessary that F is a 1 to 1 function. Okay, it's a statement. It's a statement that we need to know. Okay, any questions on this fact about 1 to 1-ness? Any questions? Before I go on to H, right, I want to investigate further about this 1 to 1 function. Okay, so guys, can you turn back on your lecture notes? Turn to example 24, if you will. Just turn to example 24. I'm going to go back to example 24. And you tell me the graphs given there, which one is a one-to-one function and which one is not a one-to-one function. Look at example 24, guys. Example 24. Gx, this one, yes, this is a one-to-one function. Okay, so one-to-one. Every output has a unique input mapping to it. Okay. Yes, H is not one-to-one. You see here, in H, just look at this horizontal line here. This horizontal line indicates that many points map to a single output 2, and similarly for this, many points map to 0. Okay, so this is actually a many to one function. So, guys, can you suggest to me another example of a many to one function? Let's say I want a many to one function. Can you suggest another example, another formula or something? The line y equals to x. Y equals to x looks something like this. It's a diagonal line. But isn't this every output has one input mapping to it? So, only one, right? Only one input maps. Let me address some of the suggestions. Some of you say a vertical line, maybe like this. But guys, a vertical line is not a function. It's not a function. Yeah, y equals to 1. This is 1. Something like this. So clearly many points map to 1. Okay, so this is not 1 to 1. I'll give you another one. Okay, let's equate all this. Y equals to x squared. So x squared is also not 1 to 1. Yep, that's right. One input to output. So it's not a function. Okay, vertical line is not even a function. So you cannot even consider this a negative one. Yeah, vertical line is one to many. That's right. You can describe vertical line as one to many. But one to many is not a function. One to infinite, in fact. Yeah, that's right. That's very true. Very perceptive. One to many. One input maps to many outputs. So that's not a function. Okay, let's just go back to example 26. Okay, everyone go back to example 26 right now. Let's go. And we look at the last one, H, and then ask ourselves, okay, is H going to be invertible? Okay, let's look at H inverse. Oops, let's get rid of this. So let's look at H inverse. Okay, and fill up the lines. Okay, let me try and fill up the lines. So 0 goes back to 1. Okay, 7 should go to 3. And let's see, where does 5 go to? 5 should go to 5. Now, guys, let me ask you, is H inverse a function? What do you guys think? Is H inverse a function? No, why not? Why not? Let's give me a reasons. Why you think the last input, right? Everyone, you notice that the last input, 2. Where does it go? I don't know where 2 goes. 2 is an orphan. Input must have an output, that's right. 2 don't know where to go. put here doesn't know where to go. So H is not, H inverse, sorry, is not a function. And so H is not invertible. Now, why does 2 doesn't have output? Why does H inverse don't know what to do with 2? Anyone can give me a reason why H inverse doesn't map 2 to anything? Can you give me, suggest any reason why H inverse doesn't know what to do with 2? Yeah, there's H doesn't have the input for 2. Very correct. That's right. 2, right? Yeah, Zhen has the best one. 2 is not in the range. Okay. Right. If you look, 5, 7, and 0, that constitute the range, but 2 is outside the range. Okay. That's right. 2 isn't. Oops, it's too thick. Let me get rid of this and write again. This output of 2, okay, this output of 2 is not in the range. And that's why when you reverse the arrows, H inverse doesn't know what to do with 2. Okay, very good, very perceptive. Alright. Now, if guys, okay, if the range of a function is smaller than the codomain, you know, I hope you still remember the codomain is 5, 7, 0, and 2, but the range is what I highlighted in blue color. Okay. Yeah, the codomain. Let me write this. When the range is a subset of the codomain, proper subset, okay, then the H is not invertible. Okay, then H is not invertible because he doesn't know what to do with the extra bit. H is not invertible. So guys, in order for H to be invertible, let me ask you what must happen. Let me write it here. Okay, just write it here. In order for H to be invertible, so what must happen now? Yeah, that's right. So in order for H to have an inverse, to have H inverse as a function, we must have that the range is equals to the codomain. And this is a very important property. Let me put a box around it. So if a function, the range of the function is equal to its codomain, we call this function an onto function. Okay. So an onto function is a function whose range is equal to its codomain. Equal. You got that? A function which is onto is when the range is equal to its codomain. Onto, A-O-N-T-O, not one to. Okay, onto, O-N-T-O. Right. So we've learned two things. Okay, we've learned two things. The first is that if a function is invertible, then it must be one-to-one, and also it must be onto. Alright. It's also true in this theorem that for an inverse to exist, so for an inverse to exist, the function f must be 1 to 1. That's the first criteria, and it must also be onto, which is the second criteria for the existence of f to the power negative 1. Alright. So I want to pause here. Alright, let's give you a short break, and I will resume my lecture at 11 o'clock. Okay, so you can go and take a short break. So I'll start again at 11. Alright, guys. Right, guys, let's continue again. Everyone ready? Let's continue with the rest of the chapter. Okay. Right, is everyone back? Are you all guys ready? Okay. Try to take this over. Right, good, 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 good. So, yeah, example 27. Okay. This is where we apply what we have learned, okay, and look at several important examples, formulas now. We can look at all the formulas. Let's look at A. 7A. I hope you still remember this notation. This notation over here, what it means. Okay, the first R is what is my not this one. The first R, the one I'm highlighting in yellow, that is the domain. Okay, I also remember that's the domain of the function. There's the second R, the one I'm going to highlight in green. Okay, what's that? Can anyone tell me what is the second R? What's that? No, Java is not a range. It starts with C. Second R. No, the word I'm looking for is codomain. Yeah, I know that is the real numbers, but the name in terms of if we're talking about functions, the second R is actually the codomain of the function. The one to the right of the arrow, the one that is the arrow pointing to, that's the codomain of the function. Yeah. Okay, so the formula for this function is x plus 2 and then everything divided by 3. So let's try and find out, we are trying to find out whether or not this function will be invertible or not. So there are two criteria to check. One, we've already said, is onto. A function must be onto before it can be invertible, and the second criteria is that it must be 1 to 1. Okay, before it can be invertible. So we have to check these two criteria before we can decide whether the function has f inverse or not. Okay, so how to check onto? Just now you told me onto is already, the meaning of onto is when the codomain is equal to the range. So we have to check the codomain of f, what it is. And the codomain of f is R, as given here. So that's how you check for the codomain of the function. How about the range of f? Okay, let me put this out to the class. What is the range of x plus 2 over 3? Can anyone tell me what is the range of x plus 2 over 3? Yes, it's also R. So since the codomain is equal to the range, f is an onto function. As simple as that. So the codomain of the function you identify from the functional notation. The range of f, you look at the formula and decide whether or not it is a certain set. Okay. So this function is onto. It satisfies the first criteria for invertibility. We have to check the second criteria now. Let me check for the second criteria now, and how will that work out? Okay, we have to check 1-to-1, and please pay attention. Okay, there's a certain procedure which is outlined here, which we need to follow to check something is 1-to-1. Now remember guys, that 1-to-1 I said already is when output has only one input mapping to it. Okay, that's the meaning of 1-to-1, right? One input, one output. So an output has only one input mapping to it. We don't have such thing as a single output having two guys mapping towards it. Okay. So when we start with output in the sentence, in the mathematical statement, we must also start with output. Excuse me. Okay. So an output means one output. So if we got FA and we have FB, FA and FB must be the same. Okay, so that's why we start here. FA is equals to FB. So, but what is FA? FA will be just A plus 2 over 3. And what's FB? FB is B plus 2 over 3. Okay. Now, just repeat again. An output has only one input mapping to it. Okay, so an output, we start with only one output. So that is why when we want to check for 1-to-1, we start with FA equals to FB. Okay, one output. So FA equals to FB, this means the same output. Okay, although it looks like got two different things here, but actually it's the same thing. And we are supposed to show that there is only one input mapping towards it. Okay, one input mapping towards it. That means at the end, we are supposed to show that A is equals to B, because remember, A and B are the inputs. So there's only one input. I know this is not so easy to see, but when we look at the equation A equals to B, this means that A and B are the same thing. And that's why it's only one input. Just as before, when we have FA equals to FB, that means FA and FB are the same thing. That means only one output. Okay. Now, how do you proceed A equals to B? Well, you have to look at the formula. So that's A plus 2 over 3 equals to B plus 2 over 3. And you see that the 3 can cancel. That gives us A plus 2 equals to B plus 2. And then again, we can see that 2 and the 2 can cancel, and that is how we get A equals to B. So if you can show this piece of working, if you can start with FA equals to FB, argue your way through or simplify your way to A equals to B, then F is 1-to-1. If you can't do this simplification, it means that F is not 1-to-1. Okay? So any questions about this? Any questions about this? I will show you with example 28 do this another time. But for now, just an introduction to how to show something is 1-to-1. First, you start with FA equals to FB. Then you try to simplify the resulting formula down to A equals to B. If you are successful, then you can say that F is 1-to-1. Okay? Because you have successfully shown that one output is mapped to by one input only. Okay, since F is 1-to-1 and onto, then the inverse of F, this is, you have already checked that it's 1-to-1. Two criteria. Once these two criteria are satisfied, that means F is 1-to-1. Okay, let's see. Okay, the next we're going to discuss is x squared. Right? once we do x square, I want you to compare the working in A and the working in B and see the differences. So because we are going to actually show that x square is not invertible. So the same thing, if you want to check that x square is invertible, we have to find the domain, codomain, sorry, we talk about codomain of G, and also the range of G. Alright guys, let's look at the codomain of G. The codomain of G is this one. And anyone describe this set to me in interval notation? What set is this? Just type up your answer inside the messaging box. What is the codomain of G? The one I highlighted, just highlighted in green. All positive real numbers including 0. If you can you type out the interval notation? Interval notation. How do you write all positive numbers including 0? Interval notation. Yeah, that's right. 0 to infinite, square brackets around the 0 because including 0 and then all the way to infinity. That's the range of, that's the codomain of G, not the range. Sorry. How about the range of G square? What is the range of x square? If we look at the graph, x square is a U-shaped graph. The range is what numbers? Is it the same as the codomain or is it a smaller set? What do you guys think? Is it the same thing or it's a smaller set? Same, that's right, answer is a same set. Same, okay? So we all know that x square is always non-negative. Square anything is always non-negative. So you write 0 to infinity. Okay, round bracket, okay, not square bracket, round brackets. So x square, we know the range is all the non-negative numbers, including 0. So the codomain is clearly equal to the range. I'm sure you all can see this. Hence, G is on to. This is an on-to function. Okay, so good. The first criteria has been satisfied. We are happy. First criteria has been satisfied. Now, how about 1 to 1? Okay, how about 1 to 1? Is this function x squared, the graph of which you can see over here, right? This is the graph over here. Is this a 1-to-1 function? Well, the answer is actually no, right? It's actually not a 1-to-1. And we can give a simple example to show that it's not 1-to-1. For example, we can look at 2 and minus 2. And we can look at their outputs. What's the output of 2? Well, G2 is 2 squared, right? Remember the formula is x squared, right? Which will give us 4. And G of minus 2 is minus 2 squared, which again will give us 4. So you see, we have 4 over here, one single output, but we have 2 inputs which map to it, 2 different guys which map towards 4. So it is not 1-to-1. I think look at this diagram, clearly shows you that it's not 1-to-1. SG is not 1-to-1. Okay, it is not 1-to-1. And in fact, you can see from the graph also, from the x squared graph, if you have a single input here, sorry, if you have a particular output here, you notice that this graph has 2 things pointing towards it. It has 2 different inputs that map towards that single output. So it's definitely not 1-to-1. So sorry, this condition is not satisfied. And hence the inverse does not exist. Okay, we saw already in previous example 26, the inverse of G does not exist. Okay, Lester, what is there a question that you want to ask? Okay, so Lester is asking a very good question. If I let GA equals to GB, can I conclude that A equals to B? Let's try this, guys. Okay, let's try this. Right, let's try this. For the time being, I'm going to switch over to my whiteboard. So I'm going to show you that you actually can't do this. Okay. Right. Switch over to my whiteboard. Okay, so Lester asks, okay, if we let GA equals to GB, can't we show that A equals to B? Alright. So here's the thing, okay? G is x squared, remember? Okay, G of x is actually x squared. So you got A squared equals to B squared. Okay. Now I know it's very tempting to take square root of A squared. You can also do something like this. Okay. But let me just say that the square root of A squared is not A, okay, and neither is the square root of B squared equals to B. Okay, if you flip back a few pages to the beginning of this chapter, you turn back to the page of your lecture notes. Okay, just turn back to page 6 of your lecture notes. Inside the theorem there, can you tell me what is the square root of A squared equals to what? There's a box theorem B. Just above example 5, page 6. Can anyone tell me? Square root of A squared actually is equals to what? Is it equals to A? Yes, that's right. It's actually equals to modulus A. The square root of B squared is actually equals to modulus B. So you can't actually successfully say that A is equals to B. It doesn't work. That's the problem here. And guys, just because modulus A is equals to modulus B doesn't mean that A. Remember that modulus is actually a V-shaped graph. Okay. Modulus is actually a V-shaped graph. So if you have a single output here, it is mapped to by two different things. Okay. You see, two different things and mapped to the same guy. So here's my A equals to B. Alright. That doesn't mean that A equals to B, alright? There are two different things that map to the same guy. So in fact, the correct way to proceed, okay, correct way to proceed from here goes something like this. You bring over the B squared, okay? It's equals to 0. And we factorize this, A minus B and then A plus B equals to 0. And we all know this tells us that A is actually equals to B or minus B. Alright, so you see it is not one-to-one. In fact, it gives you two different answers. Okay. If here is your G of A, which let's say it happens to be equal to G of B, and you see that this equation up here, shows that actually we could have B or minus B, potentially two different elements which map down to the same point. So that shows that x squared is not one-to-one. So I hope this answers Lester's question. The trick here is that you can't take square root. I know it's very tempting to take square root, but then the problem is square root of A squared is not A, okay? Square root of A squared is a modulus of A. Please remember that. Okay? So you can't simplify things like that fluently. So that's the trick there. Okay? Is this okay with everyone else? Before I go on back to example 37, is this okay with everyone? This is an important point, okay, especially when dealing with quadratic equations. Very common mistake students tend to make. Okay, let me go back to the Word document. So here's my Word document. Now let's look at the last one. Okay, over here, this one. So for the inverse to exist, the largest restricted domain of G can be equals to, okay, now we want to make G into an invertible function. That means we want to make sure that this condition is satisfied. It is not satisfied currently. On the graph so that this condition will be satisfied now. So how do you do that? This is your aspect. Yeah, you can actually take 0 to infinity as your domain instead of the whole x-axis. Your domain now is just half of the x-axis. So that what happens? The sloping downwards part of the U-shaped graph is removed, and then all you're left with is just half of the U-shaped graph. Okay? In other words, you're removing the negative numbers. When you do that, the x squared graph should become half, and then this will be clearly 1 to 1. And then you have an invertible function once again. Yeah, also can. That's right, very good. Negative infinity to 0 also can. In which case, then our graph will look something like this. Now it's the other side of the U shape. So either way, if you slice the x square, you slice the U-shaped graph into 2, then you get 2 possible inverse. You get 2 ways to get an inverse function. Okay. Are there any questions? Let's take some questions first before we go on. What part you don't understand? The codomain is given to us. It's actually given to us in the function. Yeah, you can't go from negative infinity to infinity, because if that's so, then it's not 1 to 1. So that's why you split the original domain into 2 by actually removing part of the domain. You see that you just isolate the part of the graph with, which is actually just 1 to 1. Is to answer Howie's question. Yeah, but I don't understand your question. What do you mean by how do you arrive at the codomain? The codomain originally was given out here. Okay. That was where we got the codomain already. Alright. Yeah, let's just wait for Gemma to give this question. if you let the largest restricted domain to be x squared is always positive, yes, that's true. So, but you see, yes, the x squared is always positive, but the input that maps to this positive number is only 1. It's only a negative number. That's what we want actually. Single output, there's one input mapping towards it. Okay, good. Okay, now we are going to do some exercises where actually we want to find a formula for f inverse now. Okay. So let's say your fx is given by 4x plus 1. So what is then the formula for f inverse? And I'm going to just show you the general method. It's quite, it's not that hard, and it relies on the earlier identities of f inverse which I established just now. Okay, remember just now that if we have f inverse x and then you apply f to it, what do you come out with? You come out with x. Remember? Okay. So how are we going to use this identity to actually derive the formula for f inverse? It's quite nice. See f itself, okay? Whereas f, the formula for f is 4x plus 1. Right? This is actually the formula for f, is 4x plus 1. But now what is the input to f? The input to f now is actually f inverse. So your f inverse is supposed to be substituted inside here. You see that? So into the x, I'm going to replace it with f inverse of x. So there's a quick trick there. Right? Can you see what I did? Okay. You understand this step? It's a crucial step, alright? We need to understand this step before we can go on. Okay, no questions, so just continue. So this will be equals to x, and then you try and make f inverse the subject of the equation, so that will involve bringing over the 1, so that's x minus 1, and then dividing by 4. So your formula just pops out, your answer just pops out just like that. Okay, it just comes out, no problem at all. Okay, so that's the general method in which we discover what f inverse is, and we will apply these methods to answer the example 28 and 29. Okay. Sorry guys, I think we need to extend the lecture to 12 o'clock. So let's apply our knowledge to these two functions, hx and gx. We'll do hx first, answer ABC, then we do gx, answer ABC. Okay. So they are saying that this is a real valued function. Okay. H and G are real valued functions. And that means h is a function from R to R, where hx is actually equals to 2x minus 1. Okay. I know that the codomain is R because 2x minus 1, you can input any number you like. And I know that the codomain is R because let's say here is a real valued function. So the codomain must be R. Okay, so part A, they ask you, is this H invertible? Assumes that x is definitely more than 0. Yeah, x has to be more than 0. If not, you can't take square root. But I mean, we are just doing for the h first. Okay. Then only later we do for G. So it's like doing two questions here. Later when we do Gx, then the domain of course is more than 0. X is more than 0, more than or equals to 0. But now we're doing H, so the domain is all of R. Okay, now we do A, so is H invertible? So we have to check whether it's onto or not. So onto, you just check the codomain of H. No, the domain is R. We're talking about H now. Don't try not to confuse with G. We're not doing G yet. We're still doing H first. So the codomain is H. It's actually R. Okay. You see it over here. That's how you should see it from here. Now the range of H is also R because it's a straight line graph. There is no maximum and minimum to this graph. And we see it actually from the formula. Okay? Alright, so clearly this is onto, alright? So H is onto. Because the codomain is equal to the range. H is onto. To check one-to-one, let's just run through the steps to check one-to-one. Straight line graph is clearly one-to-one, so we can use this way to prove it. So FA equals to FB. Then this would mean that 2a minus y is equals to 2a plus y. Sorry, 2a minus 1 is equals to 2b plus 2b minus 1, not 2b plus 1. Sorry, 2b minus 1. Sorry about that. It's still f. Cancel. The minus 1 and the minus 1 clearly can cancel. That gives us 2a equals to 2b. And then you can divide by 2, cancelling away the 2. 2 can cancel. And there you have it, a equals to b. So one single output is mapped to by one single input. So it is also one-to-one. So H is one-to-one. And therefore H is invertible. So part B requires us a formula. So we can use this way to do it. So H inverse X. And acted upon by H will return us X. FA equals FE. Remember what I said, we want to show that H is one-to-one. One-to-one means that one single output. Okay, so that's why we put FA equals to FB. We always start here. And you try and simplify the formula down to A equals to B. You're trying to simplify that. So here is one single output. And here is mapped to by one single input. That's what the working is trying to show. And no, because you should show it algebraically, because you can't prove anything by drawing a graph. Okay. Yeah. You must do the A and B method. Gaba, do you understand the explanation now? Okay. Okay. For this one-to-one, right, we are actually trying to concern ourselves, right, with this. When we want to show the function is one-to-one, we want to make sure that a situation like this doesn't happen. Okay. We want to make sure that a situation like this doesn't happen. If a function is not one-to-one, this kind of situation shouldn't happen. Okay. You are following me so far? Okay. You got two inputs A and B, and if they happen to map to FA equals to FB, I mean if f of A is equal to f of B, that means this is what this situation means. Okay, you have two different inputs and they map down to the same point. You need to say FA is equal to FB. Then this function is not one-to-one, alright? It won't be one-to-one. Now, this working here, all this working that I'm showing down here, this method, is a way for us to say that, hey, we are starting with FA equals to FB. Alright, we start here, FA equals to FB. And then we do the working down, and it tells me that actually the conclusion is that A must be equals to B. In other words, right, guys, if I start with an output, and my output is that FA is equals to FB. Okay, if let's say my output is called FA and it's also called FB, and I managed to show that A is equals to B, that means there is only one input which is mapping towards this point, okay? And this single input can be called A, and also it can be called B. So what was potentially two different points which map down to the single point is actually in fact just one point only. Okay? And with that, you actually show that there's one single output which is mapped to by one single input. Does that make sense to everyone? You are basically trying to show that what I box here cannot happen. Okay, this one shouldn't happen. This one shouldn't happen. There are, when you start off the working, okay, when you start off the working, A and B, their relationship is, they are just two different symbols. Okay, they are, okay, when you start off the working at this stage over here, you don't know whether A and B are the same or different. Okay, let me just say, when you start off at FA equals to FB, you still don't, you don't know. Okay, you still don't know whether A and B are equal. They could be equal, they could be different, you don't know yet. Okay, the purpose of this working, the purpose of these subsequent steps, all right, all these subsequent steps, yeah, that's right, you don't know whether they're equal, but you must prove that they are equal. If you are right, this one is right. The purpose of these subsequent steps is to show that actually A is equals to B. So it's actually derived that A equals to B, so that this situation is excluded to be in this situation. Okay, that's the purpose of the working. I hope this makes more sense. Does it make sense? Okay, Ken, I'll try my best to reply through email. Yeah, the same for the rest also. Okay. If you have the same question with Java, you can team up together with him. Then you send a group, you send an email, sort of a group email, the CC to everyone. Then when I reply, I can reply directly to everyone. So, okay, so we all do that. I'm sorry, we must go on. If not, we are going to finish at 1 o'clock. Okay. Let's we do B to find out the formula for 2x minus 1, the inverse plus inverse formula. Okay, so now I give you the wrong answer first, guys. H inverse x is not equals to 1 over 2x minus 1, okay? This is not correct. That's not what H inverse is, okay? Look at carefully how we do it. So just as before I said already, H inverse x is the input into H. So that will go into 2 H inverse x minus 1 is equals to x. Alright. Then you make H inverse the subject of the equation. And how do you do that? Bring over the minus 1, so that becomes x plus 1, and then you divide that by 2. So this is the answer. Okay. That is the answer. H inverse is not 1 over 2x minus 1. It's x plus 1 over 2. We'll come to that. Okay, we'll come to that in a moment's time. Right? Yeah. So good. Let's go to G. Then we can discuss all these questions you're asking. Okay? How to use the A and B for G. Okay. Let's do G now. So for Gx is 1 plus square root of x. Now G, the domain must be 0 to infinity because of the square root, and it's a real value function. So it goes to R. Okay, is this onto or not? So the answer A is G invertible. Is it onto? So we check. Okay, what's the codomain of G? That's R. Okay. Okay, we see from here. We see from here. What's the range of G? The range of G is actually, what do you guys think? What's the range of G? Yeah, 1 to infinity. Including 1, including 1. Not R plus, okay? I mentioned already, R plus is not the same as 1 to infinity. It cannot be R plus because X outputs minimum is 0. Okay, the minimum of square root is 0. And then you add 1. So the minimum will be 1. It's not, so R take away 0. Okay. The range is 1 to infinity. Can you see it from the formula? Minimum of square root is 0 already, so you think the minimum value is somehow at 1, so the minimum, the new minimum must be at least 1. Okay, we're starting from 1 onwards. So clearly this is not onto, alright, so it's not invertible. It's not onto. G is not invertible. Now, if we want to check one-to-one, we can do that. So just do GA equals to GB. Okay, so let's just assume that we have the same feed output, okay, but we still don't know what A and B, the relationship between A and B is. So if you look at it, this is 1 plus square root of A equals to 1 plus square root of B. Okay. Yes, the codomain of G is the real numbers. And the stated is real value functions. That means the codomain must be real numbers. Okay, let me continue. So the 1 will cancel. No, no, it's not. It's not possible. That's why I say here the range is 1 to infinity, right? The range tells you that there is no negative numbers. Codomain is everything. Okay, for the rest, the 1 cancels. And the square root of A equals to square root of B. Now, there is no problem, okay, squaring both sides for square root. So, square root of A squared is equals to the square root of B squared. And that is, so I'm just showing, okay, I'm just showing, actually no need, you can stop already. Okay, to answer Harry's question, actually, once you know it's not inverted, then you just stop. You don't have to show what you want. Okay, it's not necessary actually. Just showing for the completeness. Okay. Yeah, so actually A is equals to B, so yes, this guy is 1 to 1. Okay. It's not on 2. Alright, now if we want to make G into an invertible function, we have to modify the codomain of G, okay? If we still want G to be invertible, since it's 1 to 1 already, you just need to change the status of its onto-ness. Okay, so you have to modify the codomain of G. You can't modify the range of G, but you can modify the codomain of G. So you just set a new codomain for G. You set codomain of G to be equals to 1 to infinity. Okay, so you purposely make it equal to the range of G. Yeah. And then you are done. So the new function G is take from 0 to infinity and maps it to 1 to infinity. Okay. Okay, so notice we have a new codomain now. G, I modify the codomain, so it's purposely equals to the range. So now G becomes invertible. Okay, now G becomes invertible, and we can find out what the formula is. I just write the answer for you. You try and work out the working yourself. This will be actually x minus 1 squared. Okay. So please think of the working by yourself. Yeah, that's right. That's right. That's right. So if they want the restricted part, we just need to restrict it until it becomes onto, and also restrict it until it becomes 1 to 1. That's right. Okay, that's right. Okay, guys, I want to talk about part C for G inverse. What is the, you see G inverse given by this formula, right? Okay. What is the domain of G and what is the codomain of G now? What am I supposed to write here and what am I supposed to write here? So this is the domain of G inverse. And I'm supposed to write the codomain of G inverse. We finish with this. Okay. What is the domain of G inverse? Guys, give me a suggestion. Tell me what's the answer. Type in the message box. What do you think is the answer to the domain of G inverse? It seems like the real numbers, but no, you're not. It's incorrect. Okay, it's not the real numbers. It's not the real numbers. In fact, okay, everyone, listen carefully. The domain of G inverse must be 1 to infinity. Okay. One to infinity. It must be 1 to infinity. Domain of G inverse must be 1 to infinity. Because why? An inverse function is supposed to reverse the arrows. Okay, it's supposed to go take the original function and go backwards. So the domain of G inverse must actually be the codomain of G. Okay. So it is 1 to infinity. It is not the real numbers. Okay. Even though it seems that x minus 1 squared no problem at all. Okay. It is 1 to infinity. The codomain of G inverse, okay everyone, the codomain of G inverse must be the domain of G. Okay, so it's actually 0 to infinity, the other way around. Okay. Remember, inverse supposed to reverse arrows. Okay. So that is like swapping around the sets. Okay. Okay, just imagine if G was the arrow going from 0 to infinity to 1 to infinity, the inverse must be the arrow flip around. Okay, the arrow flips around. So that's why you have this crisscross. So the codomain of G inverse will be the domain of G. Okay, please remember that. Guys, I didn't manage to do example 29 with you. I'll do that with you on Monday. Okay, please remind me. Okay, I'll take questions. I still got 5 minutes more. I'll take some questions. Yep. Yes, that's right. True. Question, of course, will tell you what the codomain is. To define a function properly, you have to tell the codomain. And then let's scroll up a bit. So every time they ask you about invertibility, guys, they will always tell you what the domain is, or rather the domain you just see from the formula. But they must tell you what the codomain of the function is. Okay? They'll tell you, of course, the formula that you want to invert now. Whether it's 2x minus 1 or whatever. They must tell you the codomain, of course. And then if it's not on true, then you can always make the codomain smaller a bit so that it's purposely equal to the range. Then you're good to go. Okay. I guess the main point I want to emphasize, okay guys, the main point I want to emphasize is that the compose G compose F. Okay. Yeah, that's right. That's right. Yeah, that's true. That's true. That's right. Yeah. Uh, H is you don't really see the difference because everything is all the same. Right. How's everyone? So it's last reminder. Monday we do EM1 quiz and EM1 quiz for week 3. Doing a lecture notes for both subjects. Okay. And we'll finish off this example 29 on Monday. Okay. I'll see you all next week. Okay. Thanks everyone. Okay. Right. Goodbye. Have a nice weekend.